Alright, so in this video I'm going to review the upper 6th mock exam for physics. So we're going to start off with some multiple choice questions and then move on to some longer answer questions. We're going to cover a range of topics. If you want to see which ones that we have a look in the video description. Let's get started with some simple harmonic motion. So a mass hanging on the end of a spring undergoes vertical simple harmonic motion. Which point is the magnitude of the resultant force at a minimum? So the way I thought through this is the acceleration is 0 when the velocity is at its maximum, and it's at its maximum at the equilibrium position. And if the acceleration is 0, resultant force must also be 0 at the equilibrium position. So that's the center of oscillation, is another way of saying that. Okay, so next one, look comparing pendular and mass springs. So we start off with them having the same frequency on the surface of the Earth, and then the pendulum and the mass spring system are taken down a mine where the acceleration due to gravity, or g, is smaller than at the surface. So that's what we want to know, is how the frequency changes. So first of all, I'm going to put up the equations to describe the frequency. So the top equation on the left there is for a pendulum. The bottom one is for a mass spring system. Essentially, it's the inverse of the time period equations. So you can see that G is not in the mass spring system. So we know the frequency is not going to be affected. So it's going to be either C or D. And we can see that if G gets smaller, the frequency would get smaller, which is option D. So this question, when I took it from the exam paper, the mark scheme had the wrong answer. So look out for that if you're doing this one in a real paper, but this is what we should have. So we've got a particle of mass 5 grams, or 5 times 10 to the minus 3 kilograms, and it's in simple harmonic motion, and its amplitude is 0.15 meters, and it takes 47 seconds to make 50 oscillations. What is the maximum kinetic energy? So the first thing I'm going to do is work out what the maximum velocity is, and from there I'm going to work out max kinetic energy. So the first line there, we have this equation to calculate Vmax, 2 pi Fa, and we don't have frequency, we have the ability to work out time period, so I'm going to change that to 2 pi A over T. The time period is going to be 47 divided by 50, because it takes 47 seconds to do 50 oscillations. We need the time for 1 oscillation. So we can plug that in there, and we end up with a Vmax of just over 1 meters per second. And because we know the mass, we can then convert that to maximum kinetic energy, which I reckon is 0.02025 joules, or 2.5 times 10 to the minus 3 joules there. So that would be option B. Okay, so question 4, at a certain temperature, the root mean square speed of molecules of a fixed volume of an ideal gas is C. The temperature of the gas is changed, so the pressure is halved. The root mean square speed becomes what? So first of all, let's think about the relationships you've got. So at a fixed volume, you should know that pressure and temperature are directly proportional to each other when temperature is in Kelvin. The other thing you should know is that the kinetic energy is also directly proportional to temperature, and kinetic energy is directly proportional to the mean square speed, or the root mean square speed squared, like this. So putting those two things together, we know that pressure is directly proportional to mean square speed. So what that means is if the pressure is halved, that means the mean square speed has been divided by root 2, so that when we square it, we end up with c squared over 2, which is directly proportional to the pressure over 2. So that works. Okay, so that's question 4. Moving on to question 5. We've got a graph between pressure times volume, so PV, and temperature in degrees Celsius for 1 mole of an ideal gas with molar gas constant R. Which one of these is the gradient of the graph? So first of all, the equation you'll be familiar with is PV is nRT, but you should also know that that is the temperature in Kelvin. So what I've done is I've replaced it with theta plus 273, so we can essentially put in the Celsius scale we have on the x-axis. We're also told n equals 1, so we know essentially that PV is equal to r theta plus 273 r. So theta is on the x-axis, so r therefore must be the gradient of the graph because PV is on the y-axis there. Okay, so a raindrop of mass m falls to the ground at its terminal speed v. The specific heat capacity of the water is c, and the acceleration is g. Given that 25% of the energy is retained inside the raindrop when it strikes the ground, what is the rise in temperature of the raindrop? So when it strikes the ground, it's going to become stationary. So if the energy is retained inside the water droplet, that's going to be in the form of internal energy, which is raised temperature. And so the first thing I'm going to do is we know that the thermal energy we're going to use to increase the temperature of our raindrop is a quarter of the kinetic energy. And so that's going to be half mv squared divided by 4, so 1/8 mv squared. We also know Q equals mc delta T, so delta T is Q over mc. Substitute in 1/8 mv squared for Q, and we end up with v squared over 8c, which is option D. Okay, so moving on to this one. So the dashed line X shows the variation of pressure with absolute temperature for 1 mole of an ideal gas at fixed volume. So we can see it's a straight line because they're directly proportional to each other, as we saw earlier. Which line shows the variation for 2 moles of the gas in the same container? So again, bringing up this equation, PV equals nRT. We've got pressure on the y-axis, so I'm going to make P the subject. We've got T on the x-axis, so that's going to be separated. So our gradient is nR over V. So we know that R and V are constant because it tells us. So if we double n, we're going to double the gradient, which looks very much like A. So it's still directly proportional, but it's double the gradient. Okay, so which one of these following is not an assumption about the properties of particles in the simple kinetic theory? So I'm going to go through and eliminate 3 and leaving behind 1. So the forces between the particles are negligible except when the particles collide. That is an assumption we have to make. We ignore potential energy. The time spent by particles in collision is negligible compared to the time between collisions. We do also assume that, which is why we can calculate the time as the distance divided by the velocity in the derivation. The volume of the particle is negligible compared to the volume of the container. Again, yes, we do absolutely assume this because we need to make sure there's a large spacing between the particles. So those 3 are wrong, leaving us with A being the one that is not assumed there. That is actually the mean square speed, so that's the average speed squared. Okay, so a fixed mass of an ideal gas initially has a volume V, a temperature T, and its pressure could be doubled by changing its volume and its temperature to one of these options. Okay, so the way I've done this is to start off with, I'm going to say the pressure was P, and we're told the volume is V and temperature is T, and we've got a fixed mass, so N is fixed. Then what we're going to do is we're going to change these by multiplying them by some factor. So we want pressure to be doubled. So X, which is what I've got in there to multiply pressure, we know is 2. But we're also going to have to multiply V and T by certain numbers, and they might be different, so I've called them Y and I've called them Z. But we need the result of those 2 to have doubling of pressure. So when we take Y, V over to the other side, we know that Z divided by Y must be equal to 2, so that the pressure is doubled. So then what I'm going to do is for each of these A, B, C, and D, I'm going to express Z over Y. So for A, that means Y is a half and Z is a quarter, which makes Z over Y 8. And we can do the same thing for the others, and only option B gives us a Z over Y of 2, which is the one that we want. Okay, so the diagram, a bit smaller here, shows the path of an alpha particle deflected by the nucleus of an atom. Point P on the path is the point of closest approach of the alpha particle to the nucleus. Which of the following statements about the alpha particle on this path is correct? Okay, so first of all, its acceleration is 0 at P. No, The alpha particle is closest to the nucleus at point P, which means the electromagnetic repulsion is going to be the largest at that point. So it's going to have maximum acceleration at P. Again, no, its kinetic energy is not greater than P. At P, its kinetic energy will have been transferred to electric potential energy, so it will be at minimum kinetic energy at the closest point. Potential energy will be maximum at P, and then as it moves further away, it will decrease again. So again, that one's wrong. So we're left with option D being correct, and that's right because its kinetic energy has been transferred to electric potential energy. Okay, so which of the following is equal to the radius of the nucleus of, I think that's tin? No, that's Sn, I don't know what that is. And the radius of the nucleus of zinc. So to start off with, the equation you're going to need is the equation to calculate nuclear radius, which is in your formula sheet. And so what we're going to need to do is know the mass number of each of these. So that's the one on the top. So the mass number of Sb is 125. And the mass number of zinc is 64, and we're going to cube root each of those, which is why they're really nice cube numbers. So we can see that 125 cube rooted is 5, 64 cube rooted is 4, so the ratio ends up being 5/4, or 1.25, which is option B. Okay, so some particle physics. A nucleus of a particular element decays, emitting a series of alpha and beta minus particles. Which of the following series of emissions would result in an isotope of the original element? So the first piece of information you need is that an isotope has the same proton number. So we need the decays to happen such that the proton number is the same. And you need to know alpha decreases proton number by 2, because it emits 2 protons, 2 neutrons. Beta minus increases proton number by 1, because a neutron turns into a proton, electron, and an anti-electron neutrino. So we're going to need 2 beta minuses for every 1 alpha, which is what option B says. So which equation shows the process of annihilation? So annihilation is when a particle meets its antiparticle and produces 2 photons. So we can see that eliminates A straight away. And if we have a look at B, we've got a proton and an antiproton producing 2 gamma photons, so that's a winner. C is an electron meeting a proton. Those are both particles. Option D is actually the opposite process. That's pair production, where photons produce a particle and its antiparticle. Okay. So which of the following is not made of quarks? So something is not made of quarks if it is a lepton. So we're looking for a lepton here, and the only lepton I can see is a muon, which is a big type of electron, essentially. What is the quark structure for antiprotons? So a proton is up, up, down. So an antiproton must be anti-up, anti-up, anti-down, the opposite. So the diagram gives some of the energy levels of a hydrogen atom. The transition of an excited hydrogen atom from E3 to E1 causes a photon of visible light to be emitted. Which transition causes the photon of ultraviolet light to be emitted? So ultraviolet has a higher frequency and is therefore higher energy than visible. So we need a bigger energy transition than E3 to E1. So E4 to E3 is smaller, so it's not that one. E3 to E2 is smaller, it's not that one. E2 to E1 doesn't look particularly bigger, but E1 to E0 is a bigger energy transition, so that's the one that we want. Okay, so an electron collides with a neutral atom and ionizes it. Which of the following describes the particles present after the collision? So when the electron comes in, it's going to collide with an orbital electron, and that orbital electron is going to gain enough energy to become ionized. So that means we now have 2 free electrons. And if we ionize an atom, that leaves a positively charged ion behind, so that's why it's option C. Okay, so now we're going to get onto the longer answer section of the exam. So within certain limits, the bob of a simple pendulum, length L, may be considered to move with SHM of period t, calculated using this equation. State one limitation that applies to the pendulum when this equation is used. So this is where it's useful to have gone through the derivation process. So as part of that process, you will know that this approximation was used, that sine theta is approximately equal to theta when theta's in radians. So that approximation is only valid if the angle is smaller than 10 degrees. So a pendulum is in SHM if the angle to the equilibrium line is less than 10. If it's above 10, it's probably not a good model for it. So next one, we want to describe an experiment to determine the value of Earth's gravitational field strength using a simple pendulum and some other apparatus. We need to describe how we would arrange the apparatus, indicate how you'd make the measurements, explain how you'd calculate G using a graphical method, and state experimental procedures you'd use to ensure it was accurate. So it suggests drawing a diagram, so that's what I've done to start off with. So what I'm going to do is I am going to give the pendulum a fixed displacement theta, and we're going to vary the length of the pendulum and see how it affects the time period. And to measure the time period, the first thing I'm going to use is a fiducial marker to try and improve the accuracy, and I'm going to use a slow motion camera so I can accurately track the position of the pendulum as well. And I'm going to put a stopwatch in the frame of the pendulum, so on the video we can see the time and position of the pendulum. So what I'm going to do is I would set up the equipment, and then I'm going to pull back the pendulum and release it and allow it to settle into its regular rhythm. So a pendulum typically is not in SHM straight away. We need to let it swing a few times for it to settle. So that's what I do. And then I would video 10 complete oscillations. And by watching the video back, I'd pick up the start time and the end time for the oscillations and calculate the time period for one complete oscillation. So that's how I would take one measurement, and those are some of the strategies I would use to ensure it was accurate. Okay, so let's now look at how we would carry out the rest. So what I'm going to do is I'm going to change the length of the pendulum. So I would start maybe at 20 centimeters, and I'm going to go up to 50 centimeters in 5 centimeter increments. So those are the measurements I'm going to take, and I'm going to work out the time period for each of them, but I'm going to do 3 repeats for each length and get an average time period to try and improve our accuracy and minimize any random error in our results. So using the equation we were given, what I'm going to do is first square it. So we get t squared is 4 pi squared over g times L. So I've just rearranged it a little bit because I'm going to have L on the x-axis, t squared on the y-axis, which means the gradient is equal to 4 pi squared over g. So then that's going to mean that g is equal to 4 pi squared divided by the gradient of the graph, and that completes how we would describe this experiment. Okay, so then last part of this question, when carrying out the experiment, a student measures the time period incorrectly and measures the time for half an oscillation instead of a full one. So deduce the effect this will have on the value of G they obtain and explain how you get that. So the first thing I think of is, well, if they're timing half an oscillation, their time period is going to be half what the true time period is, which means their t squared values will be a quarter of what they should be. That's the first thing. So if the t squared values are all a quarter of what they should be, that will make the gradient a quarter of what it should be. And seeing as to get G, we divide 4 pi squared by the gradient. That's going to give you a value of G that's 4 times bigger than the true value of G. So that's the effect and how we'd explain it. Okay, so a different SHM question now. So we've got a simple pendulum. It's given a small displacement, less than 10 degrees, and it performs simple harmonic motion. So first off, what is simple harmonic motion? So that is defined as when the magnitude of acceleration is directly proportional to displacement, but directed towards the equilibrium position or in the opposite direction to displacement. Calculate the frequency of the oscillations of a simple pendulum of length 984 millimeters. Give your answer to an appropriate number of significant figures. Okay, so first off, this is our equation to calculate frequency, and we need length in meters in this equation, so I've divided it by 1,000 to turn it into meters, so we can quite simply get our frequency of 0.503 Hertz there. Okay, so then calculate the acceleration of the bob of a simple pendulum when the displacement from the equilibrium position is 42 millimeters. So the first thing is, you should know that acceleration is equal to minus 2 pi f squared x. That comes from the derivation process for SHM. So we know what the frequency is, and we know what the displacement is. We need to turn it into meters, which gives us an acceleration of 0.42 meters per second squared. Okay, so a simple pendulum of time period 1.9 seconds is set up alongside another pendulum of time period 2 seconds. The pendulums are displaced, I think it should be pendula actually, but anyway, in the same direction and released at the same time. Calculate the time interval until they next move in phase, explaining how we arrive at your answer. So I'm going to show you how I thought about it. So we've got their 2 time periods. So object 2 has a longer time period. So when object 2 is finished one oscillation, object 1 has done one whole oscillation, and it's had another 0.1 seconds, so it's done 1/19th of another oscillation. When object 2 has done 2 oscillations, object 1 has done 2 2/19 oscillations. So we can see that after 19 oscillations of object 2, object 1 will be at the same point as object 2. So 19 times 2 gives you 38 seconds. Okay. So moving on to some thermal physics longer questions. We've got a thermal capacity, which is basically like mass times specific heat capacity, of 1.3 joules per Kelvin. Initial temperature 20 degrees, final temperature of 37 degrees, and we've got water of 40 grams that is being used to measure. So we want the energy absorbed by the thermometer when it's placed in the water. So we're going to assume they reach thermal equilibrium and the thermometer becomes 37. So like I said, thermal capacity is basically MC. So we just need to multiply that by the temperature change of 17, gives us a Q of 22 joules. So calculate the temperature change of the water as a result of introducing the thermometer. So if the thermometer's gained 22 joules, that means the water must have lost 22 joules of internal energy. So that means Q is 22.1 blah, 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 blah. You need to divide it by the mass, divide it by specific heat capacity, and that will give us the temperature change of the water there. It's quite small, but there is a value. So moving on to some gas law stuff. So we've got nitrogen at 20 degrees, so we're going to need to convert that into Kelvin, at a pressure of 1.1 times 10 to the 5 pascals. It's in a glass gas syringe, as we can see there. The gas is originally 8.5 times 10 to the minus 5 meters cubed, but it's compressed to 5.8 times 10 to the minus 5 by placing a mass on the plunger. So the mass is going to do some work on our gas. The change in pressure of the gas occurs with no exchange of energy with the surroundings, another word for which is adiabatic. So the new pressure of the gas is 1.9 times 10 to the 5 pascals. Calculate the new temperature of the nitrogen, giving your answer in degrees Celsius. So first off, we've got a fixed mass of gas, which means we can use this expression here. We want the new temperature, T2, so I'll make that the subject, and then plug the numbers in, converting the temperature into Kelvin, gives us a temperature of 345 Kelvin. We wanted the temperature in degrees Celsius, so we subtract 273, giving us 72 degrees Celsius. So now it wants the number of moles of nitrogen present in the syringe, using R equals 8.3. So PV equals nRT, that's the ideal gas equation. So we'll rearrange it to make n the subject, plug the numbers in. The times 10 to the 5 and the times 10 to the minus 5 cancel each other out, which is why they're not there. Temperature again in Kelvin there. So I used the initial state. You could have used the final state and you'd have got the same answer. So the mass of the nitrogen in the syringe is 1.1 times 10 to the minus 4. Calculate the mean square speed, so not the root mean square speed, the mean square speed in meters squared s to the minus 2, after it's been compressed, so in condition 2. So there are two ways of doing this, that's why I've shown you first of all the two methods. I picked the second one. So the kinetic energy of one molecule is 3 over 2 kT. The kinetic energy of 1 mole is 3 over 2 RT. So that's the one I'm going to use. So essentially half times the mass of 1 mole times the mean square speed should be equal to 3 over 2 RT. So we're going to divide 3 over 2 RT by half times the mass of 1 mole. And on the bottom line there, you can see me figuring out what the mass of 1 mole is. So we've got the mass we've got divided by the number of moles that we have to give us our molar mass, and then using that to calculate the mean squared speed in meters squared s to the minus 2. Okay. So explain why the change in pressure of the nitrogen is adiabatic, which means why there's no energy exchange with the surroundings. So that's what adiabatic means. So in terms of creating those conditions, either the glass must be a very good insulator or a poor conductor, so it doesn't allow much exchange, or the process must have happened very quickly, so there's no time for heat to actually transfer across. So just out of interest to bring in the first law of thermodynamics here, so to understand what's actually happened, so if it's adiabatic, that means Q is 0, there is no thermal energy exchanged. So that means that any change in internal energy must have come from doing work. And if we remember, we had a mass sitting on our syringe and its weight force would have been doing some work on the system, which is why the internal energy or the temperature is able to increase. Okay, so explain in terms of the behavior of nitrogen molecules how gas exerts a greater pressure than it did before it was compressed. So first, I'm going to use the kinetic theory model to explain this. And these are the stages you go through with the derivation of the kinetic model to get an expression for the pressure in terms of the velocity in one direction. We haven't used the mean square speed yet. So we can see that the temperature increased from 1 to 2, which means the RMS speed of the particles has gone up. So during the elastic collisions, the change in momentum of the gas particles has increased. So the mv squared term will have increased. As we push down the plunger, the distance the gas particles have to travel, or the time between collisions, must decrease, and the surface area in which they're colliding would decrease as well. And all three of those things would increase the pressure of the gas on the syringe. Okay, so moving on to a bit of nuclear fission. So explain what is meant by thermal neutron. So a thermal neutron is when a neutron that's been released from a fission reaction has slowed down to low kinetic energy by colliding with the moderator. And there is a typical value for this, 0.025 electron volts. And the reason they're called thermal neutrons is because this is roughly how much energy a gas particle has at room temperature. Okay, so now we're going to model a thermal neutron, but we're going to do it using some pendulum and colliding with each other. So we've got two objects. We've got a hockey ball of 150 grams and a golf ball of mass 50 grams on a same length string. And we're going to pull back the 50-gram golf ball and then we're going to release it. And it tells us that it has a speed of 1.3 when it collides with the hockey ball. So its GP has been transferred to kinetic energy. And after the collision, the balls move in opposite directions with equal speeds of 0.65 meters per second squared. Calculate the height above the initial position from which the golf ball is released, ignoring air resistance. So I'm going to apply conservation of mechanical energy as we've got no external forces. So the GP the golf ball starts with will be equal to its final kinetic energy. Therefore, we can put mgh is equal to half mv squared. We can rearrange that to make the initial height, the subject, and cancel the masses. We can plug that into our equation, and it gives us a starting height of 0.086 above the collision position. Okay, so show that momentum is conserved in the collision, and the collision is perfectly elastic. So first of all, let's express the initial conditions. So its initial velocity of the golf ball is 1.3. So the initial momentum of the system would be 1.3 times the mass of the golf ball. The other ball doesn't have any momentum. Likewise, the other ball doesn't have any kinetic energy. It's only the golf ball that has kinetic energy, which we can calculate. Then what we're going to do is work out what the final momentum is. So they're going in opposite directions. So I used the initial direction as the positive direction. So the golf ball is going to bounce off and have negative velocity. And we can see that the momentum is the same. And we see the kinetic energy, once we add them together, is going to be the same as well. So we know momentum is conserved because total momentum before equals total momentum after. And we can see that it's elastic as the total kinetic energy is conserved as well. Okay, so now we want to calculate the percentage of kinetic energy of the golf ball transferred to the hockey ball during the collision. So that's what I'm going to do. I'm going to, on the top line, I've got the kinetic energy of the hockey ball, or the energy transferred. On the bottom line, I've got the initial kinetic energy of the golf ball. We can cancel the halves, and we end up with 0.75 or 75% transferred. Okay, so explain how this demo relates to the moderation process and state one way in which the collisions in the reactor differ from the collisions in the demonstration. So there are a few key differences there. So first of all, in terms of relating it to it, so the role of a moderator is to take away kinetic energy from neutrons by colliding with them, which is just like the demonstration. So some ways that it's different is in the model, we assume they're elastic. Collisions in real life are very rarely elastic. We also modeled the moderator as being stationary, which they very rarely would be. Molecules are always moving around. And in our model, the hockey ball was 3 times the mass of the neutron. We try and aim for as close to the mass of the neutron as we can, which is why we use hydrogen attached to oxygen for the process. So name the substance used as a moderator in a pressurized water reactor. It will shock you to know that it's water. Easy as that. Okay, so let's move on. So we're going to look at some radioactivity here now. So we're going to look at carbon dating. So we use carbon-14, which builds up in living organisms while they're alive, or sorry, living plants while they're alive. And then after they die, it decays to carbon-12 or sometimes nitrogen-14, and the amount decreases. So we use that for aging things. So we've got the half-life of carbon-14, and we want the decay constant. So we're going to use this equation, linking decay constant and half-life, plug the numbers in, and we get a value for the decay constant in years to the -1. So a piece of wood taken from the axe handle has 0.375 as many carbon-14 atoms as an equal mass of living wood. Calculate the age in years. So this is the equation I'm going to use, and I'm going to rearrange it to make time the subject, and we're going to end up with a time in years because our decay constant is in years. It tells us the ratio of n to n0 is 0.375. Plug the numbers in, and we get essentially it's 8,000 years since the wood that makes the axe died. Okay, so suggest why the method of carbon dating is unreliable if the sample is less than 200 years old. Well, that will be because the activity won't have changed much in 200 years. Certainly not outside the uncertainty of our actual activity measurement. So we wouldn't be able to confidently say the activity had changed over a period of 200 years. So more than 60,000 years old, so carbon dating works for about 50,000 years, but after that time, it'll be too close to background level to be able to measure its activity accurately. We would have too much interference from background. Okay, so moving on to look at some X-rays. So electrons are accelerated from rest through a potential difference of 72.4 kilovolts before they hit the positively charged anode. Calculate the kinetic energy of an electron as it reaches the anode, giving your answer to an appropriate number of significant figures. Okay, so first off, we can calculate the kinetic energy of an electron in an electric field, a uniform electric field, using this equation. So we're going to multiply the charged electron by the potential difference. It's in kilovolts, so times by 10 to the 3, giving us a total kinetic energy 1.16 times 10 to the minus 14. Pretty straightforward. Then what we're going to do is we're going to assume that this electron gives up all of this energy to form an X-ray photon, calculate the wavelength. So the equation we need is the equation for a photon energy, E equals hf, or E equals hc over lambda. Then what we're going to do is rearrange to make lambda the subject, plug the numbers in, and we get our wavelength there in the order of magnitude times 10 to the minus 11. Okay, so part B, X-rays are used in a CT scanner, or a CAT scanner as it's sometimes called. Describe how a CT scanner produces an image. So the first thing we have is we have an X-ray tube to emit a thin beam of X-rays, and that goes through the patient. And what we do is we measure the intensity of the X-rays the opposite side of the patient using a detector. So what we're interested in is the attenuation of the intensity of those X-rays, because that tells us what tissue the X-ray has gone through, and it'll have different values if it's bone, muscle, whatever. The X-ray tube and the detectors then rotate around so they can take a image from all sides of the patient, and they send the intensity measurements to a computer that builds up a 2D image. And then what happens is, as the patient moves through the detector, the 2D images get combined together to produce a 3D image, but allow the doctor to look at each individual slice so they can get a really detailed look inside the patient, but at a cost of tens of millions of dollars if you have a machine. Okay, so finally we're going to look at some cosmic physics or cosmology. So light arriving from Earth from a distant galaxy is going to be redshifted. Explain in terms of the spectral lines what redshift means. So what it means is the wavelength of the lines that we get will have been increased. That's what redshift is the increase in wavelength. So explain how the redshift is consistent with the movement of distant astronomical objects away from us. Okay, so when waves travel to an observer from an object that is moving away from the observer, the wavelength of the waves is increased, and that's called the Doppler effect. Okay, so that's the starting point here. So in the universe, objects are moving away due to the expansion of the universe, which was originally from the Big Bang, and now we think because of the effect of dark energy. So putting those two together, so the reason wavelength gets increased is because the waves have to travel further to the observer as the object moves away from us, which is what causes the Doppler effect, and we call that specifically redshift when we're dealing with cosmology. Okay, so the wavelength of a given line in the spectrum is 5.4 times 10 to the minus 5 using a lab on Earth where the object is stationary. When it's coming from a distant galaxy, the wavelength is 5.61. So we can see it's been slightly increased because of the Doppler effect. Show that this wavelength change corresponds to a frequency shift of about 2.1 times 10 to the 13 Hertz, using this speed in a vacuum. Okay, so the first thing I'm going to do is work out what the frequency is from the light source on Earth. Okay, so that's what I've calculated there. And then I'm going to use the Doppler effect equation that means the change in frequency over frequency is equal to the change in wavelength over wavelength. Rearrange that to make the change in frequency the subject. Put on the top line the change in wavelength over wavelength. The times 10 to the minus 7s cancel out, which is why you don't see them. Times it by the frequency, and that gives us what the change in frequency is, which you can see is roughly 2.1 times 10 to the 13 Hertz. Another way you could have done this is by working out the change in the frequency separately. So C over lambda gives us the frequency normally. C over lambda prime gives us the frequency once it's been redshifted. So the thing to remember here is speed of waves is not changed by the Doppler effect. And we can plug the numbers in, and again we come out with the answer here of 2.1 times 10 to the 13. And the reason they give us slightly different answers is because the delta F over F equals delta lambda over lambda is an approximation, it's not exact, which is why it gives us a different answer. Okay, so calculate the speed of the galaxy relative to Earth. So what we're going to do is, again, use a Doppler effect equation, but this time this version of it, we could have used the frequency version too. Plug the numbers in, and that allows us to work out how fast it's traveling away. So we can see it's 1.2 times 10 to the 7, so getting up to not far from the speed of light there. Estimate the distance in meters between the galaxy and the Earth, and we've been given the Hubble constant in 65 kilometers per second per megaparsec, and we've been told 1 parsec is 3 times 10 to the 16 meters. Okay, so I'm going to show you two ways of doing this. So this one's the first one. What I'm going to do is I am going to convert 1 megaparsec into kilometers. So on the left-hand side, we can start with the expression they've given us. 1 parsec is 3 times 10 to the 16 meters. So we can turn that into kilometers. Then we've got in megaparsecs, so I'm going to times 10 to the 6. And then what I'm going to do is I'm going to rearrange it to make 1 the subject, and we'll see why I'm going to do that in a second. So we know 1 is equal to 3 times 10 to the 19 kilometers per megaparsec. So on the right-hand side, what I've done is I effectively multiplied the speed by 1, which is what I've done there. But the effect of that is going to be cancelling out a lot of the units. So you can see in the equation, the megaparsecs cancel, or the per megaparsecs cancel, the kilometers cancel, and the seconds cancel, leaving us with just an answer in meters, 5.4 times 10 to the 24 there. So this is the more complex way of doing it with dimensional analysis. Let's show you the other way of doing this too. So first of all, what I'm going to do is I'm going to convert the velocity into kilometers per second. And then I'm going to stick that into the equation. So we can see that at the top there, the kilometers per second are going to cancel out. So this equation is going to give us a distance in megaparsecs. And then once we do have megaparsecs, we're going to convert that into meters by multiplying by 10 to the 6, because it's mega, times by 3 times 10 to the 16 to get meters, giving you exactly the same answer we got in the last question too. So that finishes this review of the mock exam. I hope you found this useful to review your answers and to improve your knowledge of the different topics. If you have any questions, feel free to comment on the video and ask me. I'll try and get back to you as quick as I can. But thank you for taking the time to watch.